So they had some other kind of music that was kind of like elevator music that I didn't think was quite as snappy. So they did have some other material we could pick here. So today what I want to do is answer questions you might have from last week's homework, and hopefully you folks are keeping up with me more or less. If you get stuck, please come in and see me or see the tutors that are in this class with you that are in room 177 for help. Because that's the best way, as you know, to learn this material is just to work together on it. Does anybody have questions from last week's material before we go ahead and go forward today? Don't be shy. You're supposed to be at the point where you've forgotten that the cameras are on. Okay. Anybody stuck anywhere? Having trouble? Presentation's so clear that you can just go do that homework without getting stuck?
Is there a quick and easy way to do that spring problem?
Yeah.
Because when I first approached
the one that starts, the problem that starts out with a spring somewhat compressed,
right,
and then, yeah, it's compressed, I think, as I recall, and I'll put it up here on this overhead. I believe the spring is compressed 8 inches from its unstretched state. That's what you always have to keep in mind, is what was the original length of the spring, and what you're concerned with is the distortion that exists in the spring. So keep that in mind as we do things later in the course. It's the distortion that exists in the spring. So if you compress it 8 inches, then that means there's some stored energy in the spring, and then that spring's going to rebound as it gets let go, and it's going to, as it starts to relax, it translates that stored energy into kinetic energy, energy of motion. Now, we're not addressing that issue right now. What we're addressing is maybe what the velocity is after it's reached part of its recovery, right? Okay. So probably the best way to tackle that problem, and I should probably put it up here on the overhead so the DVD has it. It's back on page 34, sitting right there, and I'll bring that in some. Here it is. So it's a 14-inch spring that's compressed to an 8-inch length, so it's got 6 inches of compression in it. And then it's released from rest and it accelerates the sliding block. They tell us the initial acceleration happens to be 400 feet per second squared, and then that acceleration decreases linearly. So what I would suggest you do to work that relatively easily would be to first of all draw a sketch of the acceleration as a function of its displacement from that initial position. So it's going to have to go 6 inches, I guess, right?
Do you want to convert that into feet, though?
Yes, that's correct. And so you want your units consistent. As a matter of fact, I'm glad you mentioned that. So this is going to be 1/2 of a foot on compression. And the reason is that initial value of acceleration was given as 400 feet per second squared. And this is a fundamental place a lot of engineering students have trouble. You all will make this mistake, and even after all these years, I still occasionally make this mistake. I will sometimes mix units, like I'd run this with inches and that with feet per second squared, and then it gets all screwed up. So the first thing I usually do in problem solutions is I make sure I get all my units on my sketches and everything consistent, and then I move forward from there. And they tell us that this acceleration decreases linearly as the spring relaxes, so we know we have a linear function here, and I'm going to take that 6 inches out of there so I'm not even tempted to use it. And so we have 0.5 feet here. And then what we want to do is write the equation of that. Acceleration, just like y equals mx plus b, and you're going to get the slope off of that, and then you're going to have this as a function of x with a 400y intercept. And you're going to put that slope in there. Okay? So that's might be where people were having trouble. Once you have that equation, then you just are going to use, this is acceleration as a function of position, so then you're going to use v dv equals a dx and solve it from there. All right? So that should work out pretty nicely and easily for you. Okay. Any other questions from homework, previous homework? Okay, I'm probably going to collect an assignment from you on Thursday of this week. It'll be one of those first 2 or 3 assignments, something reasonable. I'm not going to collect something that it was essentially material I just covered the previous day. It's going to be something from maybe the week before or so forth. And I mainly want to just look over your homework and see if you're laying it out the way that I suggested for you to do it, and the way I'll be grading it. And once again, how I grade it is I'll collect your notebooks at the time you take your midterm exams and the final, and I'll thumb through it while you're doing that and give you a grade based on neatness, completeness, steps shown, graphs embedded in your work, occasional English phrases in there describing what you're doing with each step, and each step being shown as I mentioned, and then all your work on graph paper and no more than 2 questions, 2 problems per page. Okay, it's all spelled out in the syllabus. Okay, let's go ahead and move forward with what we started on last Thursday, which was the rectangular coordinate discussion. So what we actually I didn't quite get to rectangular coordinates. What I did is we came up with the fact that we have a position vector described over here on the first board, similar to what I did with you the other day, and we derived an expression for the velocity then. And the velocity we typically write as v as a vector, and it's described mathematically then as the limit of a difference quotient, which we looked at last week. And this is going to be equal to the time derivative of the position vector, the time rate of change of the position vector as shown on the original graph over there. No mention as to the coordinate systems being used here. No mention of the coordinate systems. This is just in general. And this could be 2-dimensional, 3-dimensional. It could be a variety of coordinate systems used. Okay, next step is to do what? Which we did last week. Differentiate again, right? And we come up with an expression, again, our kinematic relationships here for the acceleration vector. And that's equal to the time rate of change, the instantaneous rate of change of the velocity vector. Okay? Now, you can contrast these vector equations with the scalar equations that we looked at also last week, where this would be our speed, or speed, we oftentimes call it v without the arrow on it, and it's just got magnitude. So you can also, this is sort of parallels. Parallels our discussion where we had the speed, which was the rate at which the length along the arc is changing, the rate of the arc length changing, and that is equal to the time rate of change, Newtonian notation, Leibniz notation. Okay? And then the tangential acceleration, which is only part of the usual acceleration we're studying, the tangential acceleration was equal to the time rate of change of this speed, which would be s double dot. And again, this is when you had the blinders on and are just looking along the path, only concerned with what's going on directly in front of you, either speeding up, slowing down, making transitions as you move along the path. Right. Okay. Now, let's come on back here and let's talk about a rectangular coordinate system. So if we come back over to the original drawing, then a position vector can be defined pretty nicely as having a x location and a y location. And we will use unit vectors like you're familiar with from physics, where we have a vector forced to stay in the defined x direction, and we typically call that I hat, unit vector. And similarly, another vector always in the y direction, and we'll call that j hat. So we could define this position vector then as being x is magnitude, I hat, plus y, j hat. So we have the x and the y coordinates there. So we'll come back over here and define the position vector as x I hat plus y j hat. Units are going to be displacement or position units, which could be meters, kilometers, miles, feet, something like that. Feel good? Okay. So typically what I'll do is we'll write vectors in this fashion. The other way we sometimes will write them, and we'll do this interchangeably, is we might use a mathematics type of notation for the vector and write it like that. And again, the units typically tagged on the outside there. Is that all right? Easy. Okay. Now, let's take the time derivative, since that's what our velocity is, the time rate of change of this position vector. And you have a product going on right here, don't you? X times I hat, magnitude times its defined direction. So when we take the derivative here, we're going to have the time derivative of x, leave I hat alone. Let's go ahead and write that down. Now, so our velocity then is going to be equal to x dot I hat. Now, I'm not going to write this other thing down. By our product rule, we would have x, we'd add to this x times the time derivative of I hat. The time derivative of I hat. Now, I hat is always pointing to the x direction. What's its magnitude?
1.
The magnitude is 1. What's does its direction change at all over time? No. So its time derivative is 0, flat out 0. That's nice. That makes the time derivative of this first term here just this. We love it. Straightforward, simple, and similarly on y dot, j hat, and now our units are, this is a differentiation with respect to time on the position vector, so this is now example of units could be meters per second. Feel good? Okay, very elementary. Similarly then, crank the next derivative and come up with the acceleration, x double dot I hat plus y double dot j hat. And again, we're dealing with the rate of change of velocity. Typically, we write that as meters per second squared, and you might want to think of it as what it really is. It's meters per second. And when you invert and multiply, that's just a mouthful. So when you invert and multiply, you get these units that we traditionally use. So that's the theory for rectangular coordinates kinematics. Now all you have to do is work a whole bunch of problems, a variety of problems involving that coordinate system to feel like you're good with it and can be almost on automatic with it. Now what I'm thinking I might do right now is go ahead and introduce, should I go ahead and introduce the theory on the normal tangential and then come back and work problems with you on both, or should I go ahead and do something with rectangular and then go to normal tangential? What would you prefer?
Let's see something in the rectangular first.
Yeah, same example.
Okay. Keep your brain kind of in an engineer's mode, plot along step by step, okay? So we'll just kind of step to the next thing here with an example. I'd like to do a generalized one. You've all done projectile motion, probably since you were blue in the face, from pre-calculus days with quadratic functions showing a flight path, right? And then in calculus, first and second term calculus, a position, take its derivative, find its speed, and all that kind of stuff. Okay. And then, of course, you've actually done these kind of problems going the reverse direction, coming from accelerations, working your way back once you got into second term calculus. So let's look at it from a vector point of view, since most of you folks are already into some vector calculus and so forth. So let's start with saying we want to model projectile motion. And I think, let me put a small sketch here, and then I'll see if I can get all the calculations over onto that other board. And we'll stick with rectangular motion. So let's say we put the particle that we're going to project as a projectile up here at some x naught, y naught location. And let me fix this. I'm going to say it's x naught, y naught down here. And the reason is I want to give it some initial velocity, v naught, at some initial angle, theta. Now, from the time we could first walk, essentially, and started throwing things around the house and then outside, we have learned that the flight path of something like this is going to follow a parabolic arc, okay? And we didn't know that vocabulary initially, but we kind of knew what the flight path looked like, right? Okay. Now, once this particle is released from rest, once we release it, let it out of our hand, say, or out of the barrel of the gun, or it leaves the bow, or you toss the package out of the airplane or something, it's under what action? Just gravity, just the acceleration due to gravity. So we're in the gravitational field, and just to make life simple, we'll stick near the Earth's surface, stay close to the Earth's surface. So what we've got is an acceleration that is g's value, and it's pointing downward opposite to the way we've defined y. So we're going to put a sign, we're going to make a vector out of that, since it is indeed directed, has direction as well as magnitude, and we're going to assign a negative to it, and we're going to make it j hat. Could also have been written as 0 minus g in that angle bracket notation. And this could be 32.2 feet per second squared, or it could be 9.81 meters per second squared. Okay, easy. So this is the stuff you see on this little picture is all we're starting with. And we want to work up the velocity. We have the acceleration profile. We want to figure out what the velocity is and then what the position is at any location on its path. You know, where it is under the action of that gravitational field and this initial condition. Okay? So we start with just that acceleration equation. And the acceleration equation happens to be right here, that the acceleration is equal to dv dt. And these are now vector differential equations. So we have dv dt is equal to this vector acceleration. We now will write this as dv is equal to, let's write that as minus gj hat dt through that substitution. And we're now going to integrate over time. Let's assume that time is 0 here, just to make the math simplest. So we'll say t equals 0. Notice how this little sketch has all the given initial conditions on it as well as the prescribed acceleration field. So we're going to integrate this from the initial vector velocity to some generalized vector velocity. Don't forget the arrowheads. If they don't have arrowheads, what are they? They're scalar values. They're just magnitudes only. And that would just be garbage if you didn't have the vector symbolism there. And over here, we're going to integrate over time, 0 to time t. Feel good? So what we get coming out the door here is that v minus v naught, our velocity, change in velocity, is equal to minus gt j hat, right? That's it. Now, when we move v naught over to the other side, it's going to be added to this term that came from our acceleration when we move the v naught over.
If we have two equations equal each other, if they're vector equations, that means that they basically have to point in the same direction. And that is taken care of by the subtraction of velocities, even though we know that the velocity at any given point isn't necessarily in the same direction as the acceleration.
Correct. But the transition in this velocity, the change in this velocity here, is dictated by that acceleration term that has been integrated over time. Because this is effectively comes from some force that actually acts on that particle during its flight path. So don't get too concerned with it at this point, but thinking that what you were thinking about is indeed true. Okay.
Mathematically, the subtraction saves us so our vectors work out.
Example, watch. Let me go ahead and put something on the picture here that'll help all of you in that thinking. After some time has passed, here's the path that's been followed over distance s, right? Distance s. And the particle's now over here, and it's carrying a velocity that we know and we've learned already has to be tangent to the path. We saw that last class session. We derived that. And so look at the transition that's occurred here from this initial velocity heading that direction with a certain value to some value over here with some different value and some different direction. And what created that was the effects of this acceleration acting over that time as the particle continually is being accelerated that way. Make sense? Okay, so now let's look at what this initial velocity is. And notice why I did not use the arrow on this v naught up here, because here's its direction. Here's the scalar magnitude of the initial velocity or initial speed, and this is the angle at which it makes with respect to the x-axis. So if I want to, up here on the side, let me go ahead and write the details of what that initial velocity is. It's made up of a horizontal component, right? Let me go ahead and put that in here. The horizontal component is v naught cosine, the adjacent side to theta, v naught cosine theta right there. And the vertical part of that initial velocity, the upward component, is v naught sine of theta. Good. So they brought the image in on the TV camera to be able to see this a little more detail here. That looks like it's coming through okay. All right. So we could write this then as v naught. I'm going to go ahead and use a simplified math notation on it. V naught is the common magnitude that can be factored out, and all I have to use is the unit vector components inside there to give its to assign the correct vector direction to that. So that's what's going to get dropped in down here for v naught when we move it over to the other side. And notice there's a j term here. There's a j term up here, v naught sine theta, that's going to be combined with this minus gt j term. So we move that over to the other side, and we get a velocity profile that is made up of v naught cosine theta I hat plus a minus gt plus v naught sine theta j hat. Units on that are meters per second, feet per second, miles per hour, whatever the problem dictates. What observation can you make by looking at this equation? Now, there's a lot of observations, but I'm looking for you to come up with one. What does this indicate to you about the motion?
Constant.
Not dependent on G, or not dependent on time.
It's independent of G, because G is perpendicular to this motion, this x-directed motion, and this is telling us that, just like you said, is that this remains constant. This remains constant. The projectile's horizontal velocity, without neglecting air resistance, remains constant. All right? Feel good? Next step. Integrate this thing, right? Come to this other differential equation now that the velocity is equal, because remember we're trying to nail down the kinematics, the geometry of the motion. We started with a given acceleration. We've now got we've nailed down the velocity, and we want to now figure out what the position is. So we have to come to this differential equation that involves the differential of the position vector and figure out what that position vector is. Ready?